Compressibility and bulk modulus. By compressibility. Compressibility is the reciprocal of the bulk modulus of elasticity K, which is defined as the ratio of compressive stress to volumetric strain. Here, to understand the compressibility and the bulk modulus, we have to first know the meaning of compressive stress to volumetric strain. Understand? For that, consider a cylinder fitted with a piston, fitted with a piston as shown in the figure. Okay. Let V is the value of the gas enclosed in the cylinder, and P is the pressure of gas when volume is V. Okay. Let the pressure is increased to P plus dP, and the volume is decreased from V to V minus dV. The increase in pressure is dP, decrease in volume is dV, and volumetric strain is equal to minus dV by V. Okay, how can we got these values means see this figure, compressibility and bulk modulus. There is a one cylinder. Okay, we are filling the cylinder and with a gas, understand, and the volume of the gas is V. Okay, when the value of the gas is V, the pressure of the gas inside the cylinder is P. Understand? During the compression, its pressure is increased from P plus dP, and volume is decreased from V to V minus dV, Go back to the previous slide. Let V is the value of gas enclosed in the cylinder, and P is the pressure of the gas when the volume is V. Let the pressure is increased to P plus dP when the volume of the gas decreases from V minus dV. Then increase in pressure is equal to final pressure minus initial pressure. What is the final pressure? P plus dP. And initial pressure P plus dP minus P. So we will get a dP. How means PP will be gets cancelled. Okay, next decrease in volume. This is nothing but final value minus initial value. What is the final value? V minus dV minus initial value V plus V minus V will be gets cancelled. So what is the remainder? Minus dV. So minus signature is keeping the term decrease. Decrease in value is equal to dV or minus dV. So volumetric strain. What is meant by volumetric strain? Change in volume to original volume. Change in volume is equal to minus dV. Original volume is equal to V. So volumetric strain is equal to minus dV by V. In strength of materials also, we had we had seen this. Yes or no? Got it. What is the thing we studied in strength of materials? Strain is equal to change in dimension by original dimension. Understand? Okay. Change in length by original length. Change in width by original length. All these things will give the definition for strain. Understand? Similarly, by using this thing, we are getting the information, compressibility and bulk modulus. Compressibility is the reciprocal of the bulk modulus of elasticity. Okay, and which is defined as the ratio of compressive stress to volumetric strain. To understand this, once again recall the terms. Consider a cylinder fitted with a piston as shown in figure. Let V is equal to volume of gas enclosed in the cylinder, and P is equal to pressure of gas when volume is V. Let the pressure is increased to P plus dP, and the volume of gas decreases from V to V minus dV. Then increase in pressure is equal to final pressure minus initial pressure. Okay, final pressure is dP, P plus dP minus P, PP gets cancelled. So dP is the remainder. So increase in pressure is equal to dP. Now the decrease in volume. Now the decrease in volume is equal to now the decrease in volume. Final value minus initial value. Final value is dV minus V minus dV minus original value minus V. Okay, if we do so, what we will get? V minus dV minus V plus V minus V will be gets cancelled, and we will dV will be the remainder. So decrease in volume is equal to dV, initiated with represented with minus dV. Volumetric strain is nothing but change in volume by original volume. Change in volume is minus dV by original volume V. So in this way we got this uh, volumetric strain. Now here we are considering the term compressibility. Negative sign means indicates the volume decreased with the increase in pressure. So bulk modulus is equal to the ratio of increase of pressure. The ratio of increase of pressure to volumetric strain. Increase in pressure is equal to dP. Volumetric strain is equal to minus dV by V. This is equal to dP by dV into V. Whole represents with a minus. Okay, minus dP by dV into V. Compressibility is the reciprocal of bulk modulus. Bulk modulus. Here we may get one term. Which one is the bulk modulus and which one is compressibility? Here see term K is there. Bulk modulus K. So bulk modulus is equal to K is equal to increase of pressure by volumetric strain. Like that we can put one hint. Compressibility is equal to reciprocal of bulk modulus, or we can write the definition for this also. Volumetric strain by increase of strain. Compressibility is defined as the ratio of volumetric strain to increase in pressure. Like that we can write it. Okay, now come for the another slide. Surface tension and capillarity. Surface tension is defined as the tensile force, acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids, such that the contact surface behaves like a membrane under tension. Okay. For example, what is the meaning of this term? Surface tension is defined as a tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids, such that contact surface will act like a membrane, and this membrane is always under the tension. Surface tension is created due to unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Molecules is in the interior of the fluid mass are surrounded by molecules that are attracted to each other equally. However, the molecules along the surface are subjected to a net force towards the interior. The apparent physical consequence of this unbalanced force along the surface is to create the hypothetical skin or membrane. Understand? Once see this figure, we can understand it. Here we are considering two molecules. Understand? One molecule is submerged in the liquid and another molecule is on the surface. Understand? 1, 2, 3. These three forces are balanced by these three forces. Understand? This molecule is experiencing the cohesive forces from the nearby or surrounding molecules. Understand? That cohesive forces are balanced each other. But Here the molecule present on the surface. Understand? These cohesive forces are not balanced. Understand? Because of these unbalanced cohesive forces, there is a net force. Understand? This net force causes a shear force. Understand? Or a tension. Understand? It forms a immiscible surface. It forms a immiscible imaginary surface in between this molecule and the surface. This water molecule is in contact with the gas, that means air. Understand? In the air and in between liquids, there is a one membrane. Understand? Hypothetical skin or hypothetical veil, and this is always under tension. Understand? How this is happening means because of the tensile force is acting on the surface. Understand? Along the length of the liquid. Understand? In which the invisible membrane is acting, and this membrane is always under tension. Okay. The tensile force may be considered to be acting on the plane of the surface along any line of the surface. See, along this line of the liquid surface, tensile force is acting. The intensity of molecular attraction, the intensity of molecular attraction for unit length along any line in the surface is called the surface tension. Okay, it is denoted by the letter sigma, and SI unit for this is Newton per meter. And surface tension is there. Okay, surface tension, we are considered two special categories, that is one liquid droplet. This is the droplet and a bubble. See, droplet has single surface and a bubble has two surfaces. Understand? Okay, consider a small spherical droplet of a liquid of radius r on the entire surface of the droplet. The tensile force is due to surface tension will be acting. See, half of a droplet, we are cutting a droplet into two halves, and we are considering one droplet, one half. Understand? If r is the circumference, sorry, radius of this droplet, what is its circumferential length? 2 pi r. Understand? Sigma s is the surface tension. Okay, sigma s is the surface tension. This surface tension is acting on the surface of this liquid, the circumferential length along the length of its surface. Understand? So surface tension is nothing but tensile force by length. So here tensile force is acting away from the surface in opposite direction from atmosphere. Pressure force is acting inside it. Understand? Pressure force will act on the cross-sectional area. If R is the area, then pi r square is the area of the half part. Understand? Delta P is the pressure. Okay, these two forces will be balanced with each other. Come for this terminology. Let sigma is the surface tension of the liquid, and delta P is equal to pressure intensity inside the droplet in excess of the outside pressure intensity. Outside pressure intensity, where R is the radius of the droplet. Let the droplet is cut into two halves. Okay, let it cut into two halves. The force acting on one half will be tensile force, and another will be forces, the tensile force due to surface tension acting around the circumference of the cut portion as shown in this. Sigma is the surface tension. Okay, tensile force is F, you just understand. Surface tension is equal to tensile force by circumferential length. Therefore, tensile force is equal to surface tension sigma into circumference. So, tensile force is equal to sigma into circumferential length 2 pi r. And pressure force is there. Pressure force. If P is the delta P is the pressure difference pressure force due to pressure difference, and this pressure difference is acting along the on a cross-sectional area pi r square. Understand? These two forces will be balanced by each other. Okay, for droplet, consider tensile force is equal to pressure force. Pressure force. Understand? Here pi will be gets cancelled, or the square will be gets cancelled. So here what is the remainder? 2 sigma s. 2 sigma s is equal to pressure difference delta p. So this pressure difference can be written as outside pressure and minus is inside pressure minus outside pressure. Okay, this and here is 2 is there. Here is 2. Understand? 2 into sigma s is equal to r into delta p, that is equal to r into pi minus p naught. Therefore, pi minus p naught is equal to 2 sigma s by r. Understand? This is the relationship between pressure force and surface tension. See, we can express this in diameters also. Here, r is equal to d by 2. Radius is equal to half of the diameter, d by 2. So what we can write the next step, pi minus p naught is equal to 2 sigma by d into 2. So we will get 4 sigma by d. So general term we have to remember in this form. Pressure difference for relationship for a droplet is equal to pressure force phi is equal to 4 sigma by d. 4 sigma by d. And go for the another criteria, droplet. This is the droplet. Sorry, bubble. Understand? Bubble is a hollow one. Inside air is there and outside water is there. Air is there. Understand? But whereas the liquid droplet, see, this is the entire liquid mass. Understand? Entire liquid mass. There is a no hollow structure for this. But whereas for the bubble, there is a hollow structure. Understand? That is why we are mentioning two lengths, two circumference. This is the thickness of the hollow structure. Understand? For this, we are showing two arrow marks, whereas for a droplet only one arrow mark. That means circumferential at circumference tensile force is acting, but here at inside tensile force is acting, outside tensile force is acting. Pressure force is acting from outside. Understand? Here, being inside circumference is there, outside circumference is there. If r is the radius of the cylinder, so inside circumferential length 2 pi r and outside circumferential length 2 pi r. So if we club these two, we will get 2 pi r plus 2 pi r. That is equal to 2 into 2 pi r or 4 pi r. That is the circumferential length. And sigma s is the surface tension. Understand? So tensile force is equal to surface tension is equal to tensile force by the circumferential length. Sigma s is equal to tensile force by 4 pi r. Understand? Consider the equilibrium, pressure difference, pressure force on the area 4 pi by 4 d square. Understand? Delta p here also. Pressure force is same, pi by 4 d square, or d is equal to 2r. Okay, once we place 2 into r whole square, 2r whole square, 4r square. 4 numerator and 4 in denominator will be gets cancelled, so we will get pi r square. And for bubble, this is the tensile force, 2 into 2 pi r sigma s is equal to pi r square dp, pressure difference for bubble. Understand? Here 4 is there and pi will be gets cancelled, r and square will be gets cancelled. What is the remainder? 4 sigma s is equal to r into dp, pressure difference. Understand? This pressure difference is equal to pi minus p naught, our inside pressure minus outside pressure, and 4 sigma s by r. Here we can consider in diameter. R is equal to d by 2. R is equal to d by 2. So we can place we can rewrite that step. Pi minus p naught is equal to 4 sigma s by d by 2. In next step, 4 sigma s by d into 2. So 4 into 2, 8 we can get. Pi minus P naught is equal to 8 sigma by d. Otherwise, for bubble, for bubble, P is equal to pressure force or pressure P is equal to 8 sigma by d. Whereas for droplet, pressure is equal to 4 sigma by d. That is the thing we have to understand. A hollow bubble like a soap bubble in air has two surfaces in contact with the air. One is inside and other is the outside. Thus two surfaces are subjected to surface tension. That is why for bubble we are getting sigma, pressure is equal to 8 sigma by d. Whereas for liquid droplet, only one surface. That is why we are getting P is equal to 4 sigma by d. Let us see one example. Let us see one example. Understand? Problem. Surface tension. Find the surface tension in a soap bubble of 40 mm diameter where the inside pressure is 2.5 Newton per meter square above the atmospheric pressure. What is the given data? Diameter of the bubble, that is equal to 40 into 10 to the power of minus 3. Pressure in excess of outside, P is equal to 2.5 Newton per meter square. For a soap bubble using what is the expression for force, and P is equal to 8 sigma by d. Understand? What is the pressure? 2.5. 8 sigma we have to calculate. Diameter of the soap bubble 40 into 10 to the power minus P. So if we calculate it, we will get surface tension as 0.0125 Newton per meter square. Understand? And another problem, let us see. The pressure outside of a droplet of water of diameter 0.4 mm is 10.32 Newton per centimeter square, atmospheric pressure. Calculate the pressure within the droplet if surface tension is given as 0.0725 Newton meter per of water. Okay, what is the diameter? D is equal to 0.04 mm. That is equal to 0.4 into 10 to the power of minus 3. Pressure outside of the droplet is equal to 10.32. Convert it into meter square. If we convert it, we will get to 10.32 into 10 to the power of minus 4 Newton per meter square. Surface tension sigma is equal to 0.0725 Newton meter. The pressure inside the droplet in excess of outside pressure is given by P is equal to 4 sigma by d. Why means this is a droplet. Understand? That is why we get only 4 sigma by d. Substitute all the values. P value 7250 is equal to 4 into sigma 4 sigma by d. Understand? If we calculate it, we will get 7250 Newton per meter square. Understand? If we want to express it into meters, means we will divide it with 10 to the power of 4 centimeter square. So we will get a 0.725 Newton per meter square. So pressure inside the droplet is equal to obtained pressure plus the pressure outside the droplet. Pressure outside the droplet, atmospheric pressure is there. So total inside pressure is equal to 0.725 plus 10.32. So we will get 11.045 Newton per centimeter square. 11.045 Newton per centimeter square. And come for the another term, capillarity, very important parameter. Capillarity is defined as phenomena of a rise or fall of a liquid surface in a small tube relative to the adjacent general level of liquid when the tube is held vertically in the liquid. Understand? Whenever if you dip or insert a glass tube of two openings, top and bottom, in the liquid, what will happen? The water level will be rises up into the liquid, into the glass tube, or the water may be liquid may fall in the tube. Understand? The property of liquid, such a property of liquid is called as a capillarity. Understand? Capillarity is defined as the phenomena of rise or fall of a liquid surface in a small tube relative to the adjusted general level of liquid when the tube is held vertically in the liquid. The rise of liquid surface is known as capillary rise, while fall of the liquid surface is known as capillary depression. Understand? The attraction, that means adhesion between the wall of the tube and liquid molecules is strong enough to overcome the mutual attraction, that is the cohesion of the molecules, and pull them up the wall. Hence, the liquid is said to be wet to the surface. Understand? If adhesive forces is more than the cohesion forces, then the liquid will wet the solid surface into which the liquid is in contact. It is expressed in terms of centimeter or mm of liquid. Its value depends upon the specific weight. That means weight density of the liquid and diameter of the tube and the surface tension of the liquid. And come for one next one slide. Surface tension regarding the one practical information. Say, consider a glass tube of small diameter d. They opened at both ends and is inserted in a liquid, say water. Okay, the liquid will rise. The liquid will rise in the tube above the general level of the liquid. See, here is a one figure. Understand? The liquid is there. Okay, both are same. Understand? Different figures. A glass tube is there. At top and bottom, it has openings. Understand? This is the general level of the liquid. Okay. Once we dip into the tube, glass tube in the liquid, what is happening? The water level in the tube is rising. Understand? Over the general level of the liquid. Understand? General level of the liquid. And the water presented inside the tube will have the concave surface. Understand? Along this length, surface tension is acting. Understand? This is the line of action of the force. Understand? The angle between the glass tube and the line of action of force is theta. You just assume. And this is the capillary rise or height of the liquid level in the glass tube. Understand? Consider a glass tube of small diameter, be opened at both ends and is inserted in a liquid. Say, the liquid will rise in the tube above the level of the liquid. That h is the height of the liquid in the tube under a state of equilibrium. The weight of the liquid of height h is balanced by the force at the surface of the liquid in the tube. But the force at the surface of the liquid in the tube is due to surface tension. Let sigma is the surface tension of the liquid and theta is the angle of contact between the liquid and the glass tube. Okay, the weight of the liquid of height h in the tube, that is equal to area in 1 minute. What is the expression for weight? W is equal to mg. W is equal to mg. See, g is there. Understand? So entire this expression is for mass. Okay, what is the relationship between the density and mass? Mass and volume. Density rho is equal to mass by volume. Okay, mass by volume. Yes or no? Density by volume. Understand? Density is equal to mass by volume. Volume is nothing but area into length or area into height. Okay, density is equal to mass by area into h. Therefore, by cross multiplication, mass of the liquid is equal to area of the liquid tube and h into density. Understand? Area of the glass tube is equal to pi by 4 d square. D is the diameter of the glass tube and h, height is the h, density rho and g. So this is the mass of the liquid presented in the glass tube with the capillary rise h. Understand? Where density is the rho and vertical component of the surface tension is sigma into circumference into cos theta. In engineering mechanics, we resolved force into horizontal component and as well as the vertical component. Understand? We just go for the back side. See, this is one sigma. Understand? This is sigma. And if we draw one horizontal direction, horizontal angle theta, or one horizontal line, this will be the 90 minus theta. Or simply, what is the vertical component here? Sigma cos theta. Sigma cos theta will come. Okay, if you want to understand clearly, means from this point, if you draw one horizontal line, we will get one angle here 90 minus theta. 90 minus theta. This is the horizontal component and this is the vertical component. What is the horizontal component? Sigma cos 90 minus theta. Sigma cos 90 minus theta. So we will get sigma sin theta is the horizontal component. And what is the vertical component? Sigma into sine 90 minus theta. Sine 90 minus theta is nothing but cos theta. So vertical component of this 4 sigma is equal to sigma cos theta. In this way, we will get it. This is one. Vertical component of the surface tensile force is called sigma into cos theta. And this is a sigma into circumference, because this is surface tension. Sigma into circumferential length into component. Therefore, what is this? 4 sigma, sigma into pi d cos theta. This is the vertical component of the surface tensile force. Understand? So, for equilibrium, these two equations will be equal. Understand? So, weight of the liquid mass equal to surface tensile force. Pi by 4 d square h rho g is equal to sigma pi d cos theta. So, if we solve the above equation for h, we will get h is equal to 4 sigma cos theta by rho z d. Next slide. Expression, the value of theta between water and a clean glass tube is approximately equal to 0, and hence cos theta will be, cos 0 will be 1. Therefore, capillary rise is equal to 4 sigma, because cos 0 is equal to 1. So, okay, this is the general expression. Capillary rise H is equal to capillary rise of water H is equal to 4 sigma by rho CD. Contact angle depend upon both the liquid and the solid. If theta is less than 90 degrees, the liquid is said to be wet. Liquid is said to be wet, the solid. However, if theta is greater than 90 degrees, the liquid is repelled by the solid. Liquid is repelled by the solid. Therefore, tries not to wet it. For example, water wets the glass but not wax. Mercury, on the other hand, does not wet the glass. One more, capillary. Expression for capillary rise. Understand? This capillary rise or fall will depend upon the density, surface tension. Okay. Here we are taking two liquids, water and mercury, in different beakers. Understand? So this is forming one layer, and this is making an angle theta here and here. So in liquid, if you dip insert one glass tube, water level will be rises up and form the concave shape. Understand? This H is greater than 0. That means general level, above the general level, capillary rise is there. But whereas for mercury, if you dip the glass, what is happening? The mercury level in the glass tube is falling below the general level of the liquid outside. Understand? And it is forming the convex shape. Understand? So this is not wetting the glass surface. The surface is repels the liquid. Understand? The expression for capillary fall. If the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid as shown in above. Okay, come for the next point. Let H is the height of the depression in tube. H is the height of the depression in tube. Then in equilibrium, Then in equilibrium, two forces are acting on the mercury inside the tube. First one is due to surface tension and acting on the downward direction. Okay, and this force is equal to the sigma pi d cos theta. Okay, sigma cos theta is the tangential force vertical component, and pi d is the circumferential length. Okay, therefore tangential force acting along its length of circumference is equal to sigma pi d cos theta. Second force due to hydrostatic force. From here, from bottom side, hydrostatic force will act. Understand? Hydrostatic force due to second force is due to hydrostatic force acting upward and is equal to the intensity of pressure at a depth of h and area. Okay, from hydrostatic force, hydrostatic law, pressure force is equal to PA. Understand? P is equal to rho g h. Understand? So what is the expression rho g h into pi by 4 d square? For the equilibrium conditions, sigma pi d cos theta is equal to rho g h pi by 4 d square. So if we simplify this expression for h, we will get 4 sigma cos theta by rho z d. The value of theta for mercury and glass tube is 128 degrees. Understand? By this we can calculate the capillary depression or level, fall of water level in the tubes. Okay, for capillary rise for water, theta is equal to 0. For capillary fall or depression for mercury, theta is equal to 128 degrees. Here that is the thing we have to remember. Here, see one more problem. Calculate the capillary rise in a glass tube of 25 mm, 2.5 mm diameter when immersed vertically in a water and mercury. Take surface tension sigma is equal to 0.0725 Newton per meter and water. Sigma is equal to 0.52 Newton per meter for mercury in contact with air. The specific gravity for mercury is given as 13.6 and angle of contact is 130 degrees. So for these conditions, he is asking us to calculate the capillary rise and fall. What is the given data? Diameter of the tube 2.5 mm converted into meters. Surface tension given for water and for mercury given 0.52. And specific gravity of mercury is 13.6. So density of mercury is equal to 13.6 specific gravity S into density of the water. Understand what is meant by specific gravity? Specific gravity S is equal to density of the liquid by density of the water. Understand? Density of the liquid means the liquid whose specific gravity has to be found. Understand? So by cross multiplication, density of liquid is equal to density of water into specific gravity. This is the applicable for all the liquids. Understand? Here what type of liquid we are considering? Mercury. Therefore density of the liquid is equal to specific gravity of the mercury and density of the water 13.6 into 1000. So we will get that value. Capillary rise for water. So H is equal to 4 sigma by rho ZD. 4 and substitute sigma density and see capillary rise for water H is equal to 4 sigma by rho ZD. For water surface tension is given as 0.0725. Density of water is 1000. G is 9.81. Diameter of the glass tube given. So if we solve it, we will get the 0.118 meters or 1.18 centimeters. Okay. And next for mercury, what is the value? Contact angle theta is equal to 130 degrees. And H is equal to 4 sigma cos theta by rho ZD. 4 into sigma 0.52 into cos 130 degrees. Rho density of mercury is equal to 13.6 into 1000 and G 9.81 and diameter of the glass tube. If you solve it, we will get J minus 0.004 meters. This minus sign indicates capillary depression. In this way, we will find out the rise or fall. See the one more problem. Find out the minimum size of glass tube that can be used to measure water level if the capillary rise in the tube is to be restricted to 2 mm. Consider the surface tension of water in contact with air is 0.73575 Newton per meter. So here capillary rise H value given 2 mm converted into meters 2 into 10 to the power minus 3. Surface tension given sigma is equal to 0.073575 Newton per meter. And diameter of the D, assume it as a D. Angle of contact theta is equal to 0 for this water. Density of water rho is equal to 1000 kg per meter cube. For water, capillary rise is equal to 4 sigma by rho GD. H value given, understand? Sigma value given, substitute. H is equal to 2 into 10 to the power minus 3 is equal to 4 into sigma 0.73575 by rho GD, rho 1000 G 9.81 diameter D. So solve this expression for a diameter D. So we'll get 0.015 meter or 1.15 centimeter. Thus the minimum diameter of the tube should be 1.5 centimeter. Okay, this is the required data. And come for one more slide. In next class, we will discuss the flow patterns and the types of fluid flows like that. Okay, right now I am going to close the session. Thank you very much. Okay, now you can leave the meeting. Thank you.